All right, hello class, and welcome to lecture 17 of our course. This will be the last lecture of the semester. Normally I teach lecture 18, which is detumbling of spacecraft, but I don't think we're going to have time for that this semester, unfortunately. So this lecture expands on or qualifies the contents of last lecture, which was stability of axisymmetric spacecraft. Right? So lecture 16 was control of axisymmetric spacecraft. This time, we're going to be talking about first, two topics really. First, which is stability of non-axisymmetric spacecraft. So still two planes of symmetry, but where we don't have that axisymmetric case. So the thing you want to be thinking of here is those Starlink satellites, right? Something that looks like that, where Ix does not equal Iy. So that's the first thing we'll talk about, case one, right? And we'll show, well, first of all, the problem with case one is that the dynamics are nonlinear, so we'll have to linearize it and consider linearized stability. And the second case, and we'll break, this is an extremely short lecture, but we'll break it up anyway, into the second case, which is where we go back to axisymmetric, although it doesn't necessarily just apply to axisymmetric, it's just the analysis is easier there. So we'll go back to axisymmetric case, right? And the two shapes, body shapes you want to be thinking of there are these prolate and oblate objects, right? So we'll qualify our stability results from the previous lecture, and with by considering the case where there's actually energy damping. So the kinetic energy now is decaying, right? T dot is less than 0. And we'll show in that case that the prolate objects are no longer stable, and we'll talk about that and give a couple of video illustrating that. So those are the two cases we're going to consider, and again we'll break it, break the video out between those two cases. Now again, this is a relatively straightforward. Here's case one, case two. It's a relatively straightforward lecture. You see there's only 21 slides. It's fairly, should be fairly quick. In the first case, they're really quite different analyses. In the first case, we're going to consider the nonlinear dynamics, and we'll show that by linearizing the dynamics, that in the non-axisymmetric case, we can have instability. So that even without energy damping, we can have instability so that a rotation about intermediate axes is unstable. And in the second case, we'll consider energy damping and how those changes in energy change the rotation axes of the spacecraft. Right. So we'll show that in particular for prolate bodies like that, if you're spinning about that minor axis omega z, well, those will eventually start tumbling, and they'll settle into rotation around a major axis. Due to energy damping. So those are two results. I've spoiled it for you, sorry, but please go keep paying attention. So we'll go through the derivation of those results. Right. So if you may remember, these are the sort of scalar versions of Euler's equations, right? Introduced in the last lecture. They are nonlinear. Why are they nonlinear? Well, because the two state variable, well, there's three state variables in here. I really should do this as a function of t. It's a sloppy notation of me. The three state variables, omega x, omega y, and omega z. Now remember what these are, right? In your body fixed coordinate system, right? Z hat, x hat, y hat, right? These are the components of the rotation vector in that body fixed coordinate system. Right? So that rotation vector, omega x, omega y, and omega z, right? And so that's the state. It changes in time in the body fixed coordinates and in the inertial coordinates, which we talked about as well. They change in time, and they're nonlinear because, right, you have the product of these two states in each term, right? All of these three equations are nonlinear. Now, in the last lecture, we were able to show that this equation becomes 0 when ix equals iy, and so this was a constant, and we were able to just sub out omega z here, eliminate it, and the equations became linear. We're not going to be able to do that in this case, however, because there's going to be changes in omega x, omega y, and omega z, right? So that's going to be our problem. So we're going to consider the non-axisymmetric case where you can't make this assumption, right? No longer valid. Right. So how are we going to analyze a non-linear differential equation? Well, the basic fact is we're not. So what do you do with in controls and dynamics and analysis whenever you're kind of lazy and you don't really want to deal with the complexity of a nonlinear differential equation? Well, hopefully at some point, if you took control systems from me, which probably none of you did, but if you did, right, then you would know that what you do when you have a nonlinear differential equation, nonlinear ODE, is you linearize it about an operating point. An operating point. What is an operating point? Well, that's the initial condition, if you will, right? The initial condition of our operating point. But that has to be an equilibrium point. So, well, okay. What equilibrium point are we going to choose, right? So if we draw our spacecraft again here, right here, well, remember that's not really the case we're considering. So let's not do that one. Here's a better spacecraft, in some sense. So we choose our z-axis carefully, right? And we're going to be considering spin about the z-axis. Spin about z-axis. Right? So that our spin is entirely, that's our operating point, our spin is entirely about the z-axis. Right? So we have an omega z here, and no omega in either of the other principal directions, right? So that our omega vector is parallel to the z-axis. Now, if you wanted to consider, this is actually spin about the intermediate axis, right? If you wanted to consider spin about, say, a minor axis, well, you would make that your z, right? And then we would line our omega vector up with that. Or if you want the major axis, you would make that z, and then we would consider our operating point would be spin about that axis. Right? So our operating point is what we were going to worry about stability of. Right? So you get to choose it, right? I mean, you get to choose which is your z-axis, and you put the spin that you're concerned about, whether you want stability of, along that z-axis, right? So that's our operating point, and there's no components of that spin in any of the other axes, right? So that's our operating point, our equilibrium point. An operating point should be an equilibrium point if we're doing stability analysis. Otherwise, right, if it's not an equilibrium point, stability is defined with respect to an equilibrium, and so, well, we can't really talk about stability at all. Right? So we're going to choose an equilibrium point. So this is an equilibrium point. Yeah, I really should prove that. And why is it an equilibrium point? Well, if you plug this omega naught into the dynamics here, right, it satisfies the dynamics for all time, right? So if you just made this a solution, omega of t, well, then this isn't changing, right? And so omega dot is just 0, 0, 0. That 0 is a little bit misplaced. Right. On the left. And then if you plug that in on the right, you get, well, this and this are both 0, so that goes to 0, that goes to 0, that goes to 0. And so the right-hand side is also 0, right? So it satisfies the differential equation. This solution, this equilibrium solution, satisfies the differential equation, right? This proves that it's an equilibrium solution. Omega dot is 0 at this point. Okay. So that's our equilibrium point. And now, to linearize, we consider deviations from that equilibrium solution. Right? So we're going to, specifically, we're going to consider motion about that nominal point. So this nominal point, if we make these vectors, right, that is 0, 0, n. Right there, n. Why did I choose n? Maybe I should have chosen omega z. Well, that's equally valid. But that confuses things, so we're not going to do that. Because there's lots of omega z's here. So we just chose an n. All right. So there's no loss of generality at this point, right? Because you can define, we're just changing our state variables. Instead of omega, the original omega, we're considering omega naught, plus delta omega. So if you have a solution for omega, you can get a solution for delta omega just by subtracting off omega naught. Right, so it's just a change of coordinates. Right. So given omega, you can find delta omega, and given delta omega, you can find omega. Right, so let's change our coordinate systems. Right. So first of all, we're going to find an expression for delta omega dot. Right, delta omega dot. What are the dynamics of delta omega dot? Delta omega. Well, delta omega dot, by definition, right, is, well, there's no matrix here yet. Omega dot, right, just chain rule here. And then omega naught is a constant, so minus 0, right? So delta omega dot equals omega dot, right? So nothing has to change here. And of course, we know the expression for omega dot. Well, here it is. Right? This is the expression for omega dot. But of course, we want to express it in terms of delta omega dot. So we're going to break down delta omega into its 3 components. Delta omega x, delta omega y, and delta omega z. And make those functions of time. Right. So we have those 3 components, and right, of course, we also have the relationship, right, that omega x of t, omega y of t, omega z of t equals 0, 0, the omega naught in its vector form, and plus delta omega x, delta omega y, and delta omega z, and make those functions of time too. Good notation. Right, so we take these expressions for omega x, omega y, and omega z, and we plug them in. There's omega x goes there, omega y goes there, and omega z goes here, right? And so we expand those out, right? That goes to that, 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 right? And we've got our initial conditions here as well, but of course this term is 0, this term is 0, this term is 0, this term is n, this term, here I should use a different color. This term is n, this term is n, and this term is 0. Right? So we get, there's no approximation at this point, right? We've just plugged in for our initial conditions, and we have a new set of differential equations in our new state variable, delta omega. They're still nonlinear, so we haven't really solved that problem quite yet. So we haven't really linearized the problem. We're just expressing it now as deviations from our nominal equilibrium trajectory. So on the next page, of course, we'll linearize, right? And how do we linearize? Well, we consider small deviations. Well, what happens when the deltas get big, right? So assume delta omega is small. Well, if delta omega is getting big, we're already far away from our trajectory, our not equilibrium, and so we're going to consider that to be unstable. So we want to know, really, for small changes in that equilibrium trajectory, whether that leads to large changes in delta omega. And once you have large changes in delta omega, of course, the approximation doesn't apply anymore, but it doesn't matter because we've already concluded instability. So we'll assume consider small delta omegas, and we'll keep the normal delta omega terms. We'll call them like small epsilon in a sense, but we won't keep the products of these two, right? Because if you have a small term like 10 to the negative 10th, and you had another term 10 to the negative 10th as well, well, that's 10 to the negative 20th, and we're going to say that is small. And so we'll approximate that as 0. It's beyond machine precision. 10 to the negative 10th is still within machine precision, and we can still solve for that. Right? So for very small deviations from the equilibrium, right, these approximations work well. Right? So there are three cases, three terms which we can get rid of this way: this product, and this product. So now if we go back to our equations of motion, right, nonlinear at this point, and we see some products showing up here, right? So delta omega y times delta omega z, that's going to go to 0. Delta omega x times delta omega z, that's going to go to 0. And this product here, delta delta, is also going to 0. And so we get here our linearized equations of motion, delta omega dot, or if we like, you can break it down into its components: delta omega x dot, delta omega y dot, and delta omega z dot. Right. Three equations of motion. Well, you may think that this looks awfully similar to what we saw in the previous lecture, that we have, for example, delta omega z dot equals 0, for example. So that implies delta omega z is a constant, of course. And then we have two sort of coupled in the same way we had before. But now we have this thing, right, where iy does not equal ix. And so the problem is a little bit similar. And of course, in the previous lecture, there was no linearization needed. Right? It was exact. Right. So we now have three equations. Right? And the third one, as I mentioned, is delta omega z dot equals 0. So as before, that implies, of course, that delta omega z as a function of time is not a function of time. It's a constant, right? It's given by the initial condition, right? Omega z initial, right? Which, if you may recall, was n, right? Not 0, n. So we've got that, and of course, now we've got these other equations here, right, which are similar, right? It's got n here, so that's also going to be omega z naught, right, equals n, but the derivation is different as from the previous lecture. Right? But in the spirit of the previous lecture, we are going to sort of combine them together and find a second-order differential equation for omega double dot of x, right? And now this actually equation, if you remember from the last lecture, this would be a lambda, this would be lambda, well, and n would be here as well, so we'd have lambda, this would be lambda over n actually. But here they're different, so we can't put them together, so we actually have to keep them separate there. Okay. So we're not going to solve this problem analytically. We're not going to do that because we don't know if we can. Basically, we don't know. Before we had this term was always positive, right? Is this term positive now? Well, we're not so sure anymore, right? Last time we knew it was, but this time last time we knew it was negative. This time we don't know if it's positive or negative, right? Because, right, last time these two terms would be like the negative of each other, and so we'd always have a negative term, but here we don't know, right? So that's the problem. So what are we going to do? Well, we are going to apply some technology, which you probably learned in undergraduate controls, which you may or may not have taken from me, probably not. So what we're going to do is take the Laplace transform, right? And we're going to get a transfer function for this system. Well, we're not going to really get a transfer function because technically transfer functions are for input-output systems, and you probably didn't learn that in undergraduate controls, but okay, I'm not gonna dwell on it. So anyway, we take the Laplace transform of the system, right? So our double dots come out as s squareds, and nothing really happens to this side over here, except of course that our variable is now a function of the Laplace variable s in the sort of Laplace domain. Not really a frequency domain because that's a Fourier transform, but we won't get held up on the nitty-gritty here. So going from this Laplace transform state, we're going to solve for the characteristic equation, the transfer function of the system, by isolating all the terms which multiply g of s delta omega dot s x of s. And of course on the right hand side we have 0 here, so again this is like not really an input-output system, so we're going to like sort of sweep that bit under the rug. It's a stability analysis, but we can do stability analysis with the transfer function, so that's just fine. Okay. So here's our transfer function here, g of s, right? You may have learned at some point, right, that the stability of a system is given by the roots of its characteristic equation, or specifically the poles of the transfer function, or the roots of the denominator, as you will, right? So you probably drew your root locus, for example, and we had the imaginary part of s and the real part of s. That looks like a b, real part of s. And we would plot the roots of the characteristic equation, the roots of the denominator, the poles of the system, right? Where are the poles of the system? And so we learned, right, that if there's a pole of the system in the right half plane, the system is unstable. And if all the poles are in the left half plane, the system is stable. Unstable, stable. And technically, right, input-output theory says that roots on the imaginary axis are sort of unstable in the h infinity sense, but we're going to sweep that under the rug again, and we're going to call that imaginary axis neutrally stable. So where are the poles? So the poles are the roots of the characteristic equation, right? There's a characteristic equation. We want to solve its roots, for its roots. Fortunately, this is just a second order quadratic equation, and so we can apply the quadratic formula. Right, to find the roots analytically. Right, so the roots are here. Okay, where are those? Well, you know, these roots have the form a plus bi, right? So the imaginary part is b, and the real part is a. Now, if you look at this, right, the question is this term imaginary or is it real? Right. Well, the answer to that, of course, depends on the sign of whatever's in the square root. So is this positive or negative? And so that's basically the question we're going to be asking. Right? So if this term here under the denominator, and here we'll focus on this because, right, well, obviously n squared is positive, and these terms are both positive, right? So the question is this greater than or equal to 0 or less than or equal to 0? So if it's greater than or equal to 0, well, when you take the square root, that's a real number. And it's going to be a positive real number when you take the square root. And then there's this plus or minus here. So if this is greater than or equal to 0, you're going to get poles here and here. Right? That's that case. Right? By contrast, if it's, change color here, if it's negative, right, well, then the whole term is going to be imaginary. And so you're going to get a pole here and a pole here. Right? And so, of course, if there's even one unstable pole, the whole system is stable. So this green case is going to be unstable because it has an unstable pole. And this other case, when it's negative, is going to be stable because you're on the imaginary axis, so technically neutrally stable. Well, that's not really technical because we don't have such a thing, but okay, we're ignoring that for the moment. Right, so as I was saying, there are three different cases, right? So there's instability if the real parts of the roots of the characteristic equation are real, right? Stability if the real parts are less than 0. So this, again, corresponds to the left half plane. Oops, sorry, that's right half plane. And that only has to hold for any root, right? Repeating myself. This is the left half plane. So stability if all of the roots are in the left half plane. And neutrally stable, right, if any root is on the imaginary axis, and none of them are in the right half plane. So if the real part is 0, and there are no other poles on the right half plane. But of course, there's only 2 poles, so it's not going to be a big caveat here in our case. All right. So if we look at the, again, roots of this characteristic equation, now we can break it down into several cases. Right? And so again, bringing it back to, right, the problem definition, let's draw our satellite again. Right? Remember, now you've chosen x, y, and z, or x, y, and z axis, or in particular, you've chosen your z axis to be the axis you are spinning about. So let's take case 1, for example. Case 1, where iz is greater than ix, and iz is greater than iy. So that means we've chosen z to be the major axis. So that would be the case where z hat is the major axis, right? So that's it's greater than ix and iy. So we don't care which is ix and iy. We only care that we've chosen our nominal spin condition, our equilibrium point, to be spin about the z-axis, the major axis. So in this case, right, iz is greater than ix, and iz is greater than iy. So if we look at this equation here, well, we've got this term. Well, remember, this is positive, right? Iz is greater than iy, so that term is positive. And this term, iz is greater than ix, so this term is negative, right? Because this is larger than this. So this term is more negative than that. And so we have a positive times a negative times a positive times a positive, or divided by a positive if you like. And so the whole thing, right, the whole term in this case overall is going to be negative, right? Or let's make it strictly negative just to make life easier. And so in this case, in case 1, spin about the major axis, the roots are purely imaginary, right? And so purely imaginary meaning that they have the form plus or minus IB, where B is this term right here. Right? So if we draw again the root locus, right? We're going to have poles here, and here, right? So that's neutrally stable. So case 1 is neutrally stable. That's spin about the major axis. And it's, we said it was stable, right? Well, I guess I didn't say that, but stable. I'll say it now. Or neutrally stable. There we go. Case 2. This is the case where we've chosen, here's our satellite again, chosen to call the z-axis the minor axis. So in that case, we've chosen z to point this way, right? Aligned with our initial angular velocity vector, right? And in this case, we have that iz is less than iy, and so iz minus iy is negative. Iz is less than ix, and so ix minus iz is positive. And so again, we look at this case here. We've got this term is negative. We're swapping the cases. Well, let's make it strictly negative to be concise. That term is positive. That term is positive. That term is positive. And so the whole thing, right, in this case, is negative again. Less than or equal to 0. So in this case, again, right, we've got roots of the form plus or minus IB, where IB is this term here. Right? So we draw our root locus once again. There's our root locus. Again, we'll have poles on the imaginary axis, and so we conclude that from this we have the case of neutral stability. So spin about the minor axis, neutral stability. Okay. So, okay, good. Doing well so far. Now, we have the third case, and that's the intermediate axis. So in this case, hopefully you've taken all the notes you need. If not, you can reverse this, right? Spin about the intermediate axis means that we've chosen our z-axis to be this one, and our initial angular velocity vector aligned with that. Right. And in this case, that moment of inertia of the z-axis is less than the ix, which would be the major axis in this case. Need some color contrast there. So in that case, the major axis, the big one, is x, so that's x. And let's make our right-hand coordinate system x, z, y. So in this case, right, y is the minor axis, x is the major axis, z is the intermediate axis. And in this case, well, if we examine these terms again, right, well, iz minus iy, well, y is the minor axis, so that's positive. And ix is the major axis, so this is also positive. Right. So now if we go back to our equation over here, our characteristic equation, we alter the situation slightly. So ix minus iz is still positive. N squared and these terms are still positive, but this term now is also positive. Right. And so what that means is that when we can take this square root and the result is a real number, a. Right. And so our roots have the form here, s plus or minus a, where a is this big term here. So in this case, our roots lie here, right? This is plus a, and this is minus a, right? And so in this case, and I should change my color maybe. In this case, right, there's a. Right? In this case, we have a pole in the right half plane, and so we are unstable. We have a single pole in the right half. We have one in the left half plane, so that one's stable, but you only need one pole in the right half plane to be unstable, and so we are unstable. Unstable. So spin about the intermediate axis is unstable. Spin about the minor axis, neutrally stable. Spin about the major axis, neutrally stable. Spin about the intermediate axis is unstable. Well, what does that mean? That means that if you start your initial angular velocity vector spinning about this intermediate z-axis, which is now intermediate, it will grow, right? It'll grow until our small deviations approximation no longer holds, and after that we can't really predict the motion. But we know the stability, we know that it's unstable. So if you actually want to see what, visualize what happens beyond the that small region, so we can use these pole hodes. So I don't know where the name pole hodes come from. I haven't done my research on that one. But what these illustrate, right, is so this is a sort of a non-axisymmetric spacecraft. I guess it's a spacecraft. It's an ellipsoid. So in this case, right, we've got the this is the minor axis. This is the major axis, and this is the intermediate axis. And so what this illustrates is the rotation vector in the body fixed frame, right, for constant energy and constant angular momentum, right? So these lines, right? So what that means, right, assuming that energy and angular momentum are conserved, right, conserved, and fixed energy, constant angular momentum, right? So assuming energy is conserved, what that means is that, right, well, you'll be moving along these lines. How quickly you move along these lines, not clear, but you'll move along these lines. So if you start at some small deviation from the minor axis, you'll just make a little circle around it. Start some small deviation from the intermediate axis, the major axis, you'll make a circle around it. And I don't know the direction, but that's counterclockwise, so let's hope. And then if you start at the intermediate axis, well, there's no little circles here. So you start a little bit off, even a microscopic bit off, right, say in this direction, and you'll float off in that direction and maybe come back here later on. Or you'll float off in this direction and come back later on. Or if you're like a little bit off in sort of another direction, let's make another line. So let's get close here. And then like that, and then come back in like that. Right, so this is what you'll be doing. You'll be going off to the side, coming on that side, going off that side, coming back on that side. And so you'll do this like weird sort of a slope shape, right? And you'll keep doing it, right? You'll keep like doing this flip, right? So the angular velocity vector in the body fixed frame will start closest intermediate axis, and then it'll like migrate off sort of halfway between. It'll do it very quickly, actually. It'll migrate halfway off between, so it'll be slow here, and then pick up speed and fast here. And then it'll slow down again, right, and pick up speed again, right? And we'll see that on the videos, right? So that's what will happen. Now, of course, on the other side, right, we can also do that. Same thing applies. So, right. So that's what happens to the angular velocity vector in the body fixed frame. It sort of starts near the intermediate axis, sort of goes between these other two axes, and then comes back and keeps repeating. And you can apply these to the other Paul-Hodes over here. For these are weirder bodies, so we just won't pay much attention to them. Right? So this is like an unstable sort of intermediate axis. I don't know, it's going to go somewhere over there. Yeah. So we can see these in a couple of videos. There's like, the internet is full of tons. So I'm gonna, this is Garrett on the space station, I believe. But I'm gonna mute him just because, well, I don't know. I like talking. So here we have a spin about the major axis, right? This is a non-axisymmetric case. There are three distinct principal axes. So that's spin about the major axis. Nice thing about space is like you can sort of visualize these pretty well. So that's spin about the minor axis, what he's doing right there. Now he's going to try spinning about the intermediate axis. And what you should see is that that angular velocity vector in the body fixed frame, the rotation angle, is going to flip at some point. I didn't do that very well, did he? There it goes. It flips, comes back to the intermediate axis, and then flips again. Flip, flip. You can see it sort of like slows down when it gets near the intermediate axis and very quickly reverses. And you can see like it goes from one side of the Paul-Hode to the other, one side of the body to Richard, do that again. Right. So notice that like it goes from one side of the cards to the other. So it starts on one intermediate. The spade is facing us. Come on, Rich. Then the other so. Right. So spade is up, spade is down. All right, see that? Spade is up, spade is down, spade is up, spade is down. So it's flipping sides, right? That rotation vector is flipping sides. All right, let's leave Richard behind. And we'll, let's see, here's another International Space Station video. Right? I think I like this one even better, but again, pay attention, right? Here's spin about the minor axis. Engineering thermodynamics. Not sure why I brought that up. Spin about the major axis. Now, hopefully we'll see spin about the intermediate axis. Any day now. Yeah, we got the major axis. Are you going to like bump into the wall or something? Danger of bringing books. Here we go. Intermediate axis. Tidal is up. Flips. Tidal is down. Flips to the other side. Tidal is up. Flips to the other side. Tidal is down. Flips to the other side. Tidal is back up again. Right. So you see him migrating from one side of the body to the other, and then coming back again. And we have a simulated example, which isn't as interesting, but we'll just play it anyway. Right. So here we got spin about the intermediate axis, right? And here, mostly intermediate axis, and then it's going to rather quickly, right? It spins there for a while, and then it rather quickly shoots over to the other side. So we'll see the pink dot be replaced by the green dot. And there's the green dot again. And we'll see it destabilize about that axis and flip over again to the pink dot on the other side of the body. Right. So you can see the motion along the Paul-Hodes is rather speeds up and slows down. So that, in a nutshell, is the instability of the intermediate axis result that we emphasize. We've proven. So we're going to cut off for a very brief break, and then we'll come back and talk about why actually, in real life, you never want to spin about the minor axis, and we'll talk about why not. So I'll take a really quick break here. Probably the shortest video I've recorded so far.